And share my screen. Okay, as I said, today we'll try to calculate some practical tasks, and we'll start with um, systems inertia. Okay, I'll use this book. Yeah, this book is in Latvian, but I'll
Language.
try to translate what is going on here. First of all, as we discussed last time, yes, we could represent a concentrated power system for one generator and one united load. So in this scheme, we could see that there is a turbine and this one is a regulator. This one is a generator and here P is a load. Yeah. So here it could be, as we discussed, main two types of electricity production generators. So if we use steam or if we use water. So steam turbine or water turbine. So in this case, the primary energy source, then turbine, steam turbine or water turbine that rotates the generator. And in this case, we have the regulator, yes, to control our, yes, control unit to control our turbine power, to control generator power. Yes, so we control turbine power with this valve and adding steam or water. Yeah, in this case, if we have the rotating elements, we could say that we have an inertia because we have a kinetic power of rotation. In this case, the formula 4.1 about this rotation, where this J represents the inertia moment in a time, where the M is turbine mechanical moment and ME is electrical moment and MA is representing total moment, yes, of this process, because we have two units, mechanical turbine and electrical generator. If we, no, I don't want to waste time about how we could
Derivation.
but we need a result, all of this. And the main result from here is here. So yes, we could represent the inertia using H letter in megajoules divided by megavolt amperes. So we call inertia or with H letter, or we call inertia using T letter. It depends on the country, it depends on the author, but because we could represent inertia in two units. First one, as it is here, it is megajoule divided by megavolt amperes, and we could represent inertia in seconds. Okay, for example, this table is for Soviet generators. As I said, Latvian hydropower plants was built and reconstructed. Okay, two of them was built in Soviet time. One was built before, but all of them was reconstructed in Soviet time. So it means that all of them have turbines made in Russia. And for example, for the reconstruction, for the new reconstruction, for now, yes, till the last years, all the reconstruction was made by Russians as well, because all of these power plants was developed in Russia, yes, and was made in Russia, all these units, aggregators, and so on. That's why these units with these parameters are still reliable, yeah, and feasible. In this case, we could discuss we could talk about the inertia in two ways. If we talk about the seconds, we represent inertia in seconds, or we represent inertia in energy units. Yes, this one. And we okay, I lost. Okay, this one. And their values, not units. Yeah, we okay. This sorry, these values. Oh, if we talk about h, yes, it means that t is twice bigger because different units. So this is the main dependence. Yes, t and h. In this case, when we are modeling our power system, we need to understand what is the inertia for the whole power system, what we're talking about, because it is very important to understand for us the speed of process. Because if we have some cases, okay, new idea. Sorry, maybe it will be more clear with the one more idea. So each time in power system, yes, the how to say, the amount of load is different every second. We understand, for example, you are going to a kitchen and switching, I don't know, the microwave, yes, or switching off.
Yeah.
Okay, switching on the light, switching off the light. Every time something happens, yes. This is transfer process, yes. In this case, all the time, yeah, there are fluctuations of a load. Of course, someone switches on, someone switches off. In this case, the value, not the total demand is approximately not fluctuating, yes, every second with a high amplitude. Yes, it's more or less clear. But there is an important moment. The speed of the process, of all the process in the power system. For example, I switch it on a powerful load, for example. Yes, my neighbor switched on a powerful load. In this case, for this second, we have, for example, a deficit, yes. But when we will see this deficit in the power system, because the main parameter that shows the balance is frequency, as we discussed, yes. If frequency is up, we have too much generation. If frequency is down, we have we don't have enough generation because we have a big consumption. So in this case, if we controlling power system, if we're analyzing power system, if we're modeling regimes for power systems, it is very important to understand the speed of process in our power network. Of course, it is clear that if we have a huge drop, for example, of a generation, yes, the speed of frequency decrease will be much higher when this frequency decrease if we have a very little deficit. Yes, so the amount of deficit, how big this deficit is, provides the different speed of frequency fluctuation. But whatever happen, this inertia is the main parameter that impacts, yes, the speed. So first of all is the value of deficit, and the second is inertia, yes. So in this case, the first our task for today is to calculate the inertia for the power system. how we could do it. This is a very simple task because every generator has its technical parameters, yes, from the manufacturer. And we know from the name of each generator its own inertia. Yes, for example, there are this table with several generators with its own inertia value, because it is not a secret information, because every generator is a huge metal piece, and this metal piece has an inertia. For some generators, for example, if we could say what it we could find, for example, information, yes, for its inertia, we could use some tables like this. For example, this is the average values, yes, for different types of generator. If we use CHP for the generators for CHPPs, yep, steam generators, yes, for condensing CHPPs, if it is its rotation frequency is about 1800 rounds per minute, so this its inertia could be this. If the rotating speed is twice bigger, the inertia could be this one. Yes, the same is for the hydropower plants. Yes, so depending on its rotation speed, the inertia could be in number in these limits. Yes, 2 to 3, 2 to 4, or something like this. So if we can't say the precise value, we could use an average, yes, for this. Okay, this is how we use, but what about the formula and what about the calculation? So if we need to represent the inertia of the whole power system, we need to calculate inertia based on each generator in a power system. That's why there is a formula point 12, yes, where the T, the same as H as we talked previously, is the name of inertia, and it is equal with the sum, this is the sum, yes, of the inertia of each, sorry, not each, every, for every generator, multiple by this generator power divided by the total power of all generators. In this case, there an example, a simple example. Okay, small power system with only 2 generators. The first one with the power of 500 megavolt amps, and the second one with 1333 megavolt amps. Yes, nominal voltage of 20 kV, so it's a mid voltage level, and inertia for each one, for the first one is 4.8, and for the second is 3.27. So using this formula, 4.12, yes, first of all, we calculate the total power of a system, total generation. So if we have only 2 generations, it means that we sum only these 2 values, and we got the total power of system is 1843 megavolt amperes, and calculate this part as a multiplication of each generator inertia to its power divided by the total power. In this case, for the first one is 4.8 multiple its own power of 500 and divided by the total
power.
Yeah, and the same for the second one. And when we got this, how to say, inertia for each part, yes, we make a sum, yes, and just sum of these 2 parts. I think this is quite clear. And for your home task, you will have the same task, yes, but maybe the number of generators will be 3 or 4. So just using this formula, yes, and using this video, or you could write this formula to your note, you could calculate your home task. I think this is very easy, yeah, but very important. So making this calculation, we could say what is the inertia for the whole power plant. Of course, we have hundreds or thousands small generators in a power plant, but as we saw, for example, when we from this transmission operator homepage, yes, the main generators always are very big, and all hour, as it was all hours, thousands and hundreds with a small power of 30 megawatts, yes, when we are talking about the gigawatts of power, yes. So the number of big generators is always not so big, yes, and they're making more of 90% of the whole of the all power system. So the number is about, okay, for small system it's might be 10. For a big one, really big one, it could be 100, but this number is not huge. It is quite easy to calculate, yes, this value of inertia. Okay, this is the first what we are going to discuss today. If it is clear, if you don't have questions, we could go next.
We can go next, Professor. Yeah, it's clear.
So the next what we are going to discuss, it's statism. It's a static, you know, it's a static and dynamic systems. I think you should know from bachelor degree what is static and what is dynamic. Yes, a static process or dynamic process. Yes, dynamic process that is with changeable parameters in a real time. Static process, it's mean that you have the same parameters in real time, but we are talking about the static. Why? Because this is how we could control our generator. And if we are going to control this generator using the okay, I'm sorry, just words go out from my mind. By this straight line, yeah, we call it a static because it is straight, yes,
Yeah.
without any fluctuation, yes. So that's why we are going to discuss about the static regulation, static control. What is this? What is this curve? Let's go back maybe to no, it was not here. It was in the part 1. It was here, I think, yes. It was here. It was in okay, where it is. Oh, it was in there. Okay. Okay, it was here when what we was discussing last time, the scheme and the representation. Yeah, so when we represent this concentrated system, yeah, with a steam, with a valve motor, yes, there is a control here. This unit represents the control. And if we come here, scheme, I call all these units one more time. So this was our generator. This was our power system. This is a turbine. This is the valve. This is the steam. And this is rotation control. And this is that we monitor this power system values, in this case frequency, yes, to understand what is going on, is it in balance or not, yes. So for this case, the regulator task is to increase and decrease the power of concentrated generator to keep the system in balance. And this is the question, how we could regulate this generator. In other words, we need to understand if we have a deviation of a frequency, how we could represent this frequency deviation in megawatts. In other case, if we have frequency deviation, for example, of 1%, yes, how much power do we need to increase or decrease to keep the system in balance? In this case, this static control, where it was, okay, no, okay, it was, okay, yes, it was here. Nope, this is. Okay, sorry, I wanted to start with this. So in this case, here we could see power of P and omega. Omega is 2 multiple by P multiple by frequency.
Mm-hmm.
Okay, this delete. So omega is 2 multiple P multiple
P,
frequency.
yeah.
2 by 3.14 multiple by
50 hertz.
frequency of 50 hertz. Yes, in this case, we could calculate this value 2.3. Yes. And here we could see the dependence, yes, for the regulator.
Mm-hmm.
This dependence, of course, is set, yeah, to the generator control. What the frequency? No, okay, this is not frequency, this is the angle speed. Yes, it calls angle speed, but this value depends only on frequency, because you see this part is a constant. Yes, so really it's a frequency. So what the difference in frequency, yes, means what is the difference in power. So this curve shows this difference, and these curves let us to regulate our generator. If we have frequency deviation, for example, of 0.2 hertz, it means that we have deficit of power, for example, for 100 megawatts. And in this case, it means that we need to produce more than of 100 megawatts. In this case, this coefficient, if you remember from school math, I just show very simple. Sorry. Very simple drawing of Y and X, and Y is equal to K multiple by X, yes, and this K, yes, shows, yes, this angle, yeah, because this is a triangle. If you can, we could construct a triangle, yes, with this angle of 90 degrees, yes. And in this case, this coefficient, yes, shows this angle for us, yes. And in this case, if we come back to this scheme, yes, this is coefficient, what we call a K static, yes, represents this curve. Why this is important? Because in this case, we could understand what is the possibility of each generator, yes, to react in a case of frequency fluctuation. For example, it is normal that we keep the reserve of power of each generator to be possible to increase or decrease power. Of course, to decrease power, it's not a problem. The most problem is to increase power. So if you want to increase power, yes, so you should keep this reserve to be possible to increase power of production. In this case, we keep this reserve for regulation. It is approximately 3 to 7%. Basically, if we use hydro generator, it's more about 5%, no, plus minus, yes, but it's about 5%. If we are talking about steam generators, no, CHPPs, it is about 3%, yes. And here you could understand, for example, if we have a power, yes, of, for example, 100, and we have this okay, reserve of 5%, it means that this case we come back to this unit, yes, that represents this part of regulation. Yes, it is 1 divided by R. In this case, it is 1 divided by 1 divided by its value. So I can't delete this and explain using. Okay, so if we are talking that we have about deficit, okay, not deficit, but we have a reserve of 5%, yes, it means that this regulator represents the value of 0.05. This unit from control theory, if we have reserve of 5%, yes, this one.
Yeah.
And if we are talking about this curve, yes, because this 5%, how it comes here, we have a formula. Here we have a formula. This coefficient shows us, I zoom in, so shows the equation of delta F, yep, frequency difference of fluctuation from the nominal value divided by the nominal frequency multiplied by the nominal power divided by the difference of power. So here you could see difference of frequency, difference of power, 2 nominal frequency, 2 nominal power. And here we got how we could find this, yes, coefficient, how it is. Okay, but here, very simple formula. This will be useful for you. You could write this formula to your note. But this formula is for one generator, this. For example, but for the concentrated one. But what to do, as we saw previously, we could calculate the total inertia, yeah? But what about this total coefficient to understand what is the reaction of the whole power system to the frequency fluctuation? In this case, we have okay, this drawing. Here you could see the system of 2 generators, the same drawing. The difference is that here we could see the frequency, not the angle speed, but the same, yeah, just not using 2 multiple by p. And here we could see, because we have different curves, yes, different angle for curve, yes, because different coefficient for each generator, for each power plant, yes, and this, as a result, different reaction on the frequency deviation. So the frequency deviation is the same because the frequency is the same in the whole power system, and the reaction of each generator is different. For example, here you could see the delta P is this one, and for the second one, because this curve is different, this coefficient is different, is this one. And in case if we want to calculate them this coefficient for the regulator of the concentrated power plant, we need what to do? We need to calculate its average value, we could say in this. So for the first one, we could write this delta P is equal to delta F divided by F basic, no, yep, 0, so base frequency, yes, multiplied by this first generator power divided by its coefficient, the static coefficient. And the second one the same, using its second generator power and second generator this static coefficient, yes, as which one represents this curve. So we have these two equations. And as we understand, for the whole power system, the power deviation is equal to this power. Okay, the power deviation, sorry, I could say in another words, this power deviation is how to say divided by these two power generators, because we cover the leak of power, yes, by each generator. First one, for example, based on this curve, increase its power on for example 100 megawatts, but this one increasing its power by 200 megawatts. And this means that we cover the leak of power with total 300 megawatts. So this formula represents that our total
power.
total power that we need to cover. So total power and how this power is divided by the two units, yes, based on the static coefficient that is programmed in each unit. So, and in this case, we could their formulas. Okay. So their formula, if we, okay, there, this is a basic. And if we want to calculate, for example, if we something don't know, any parameter, for example, okay, if we don't need this, we know the total deviation, and we need to calculate what is the reaction of the first generator. This is the formula, yes. The same could be if you want to calculate the reaction of the second one with the total, if you know the total deviation and if you know this static coefficient for each generator. But as I said, this, if we want to calculate the average, this static coefficient for the power system, not for each generator. Yes, we need. Okay, we need this formula. So this formula represents how we could calculate what could be this static, this curve. Yes, what will be this curve for the power system, which is represented with one concentrated, the same as it was with the inertia, yes? And this, in this formula, E represents the number of each generator and each generator power divided by each generator power divided by its static coefficient. So this, how this could be represented. So, and if we don't know, for example, any one parameter from these formulas, yes, we could find it, yes. Because if you know total, we could understand how it is divided by two units. If you know any information about the two units, we would calculate the total impact. That's why this all possible formulas that could be used are represented here for this case. Okay. And for example, this graph represents how it is going. For example, here we could see, if we see the frequency drop, it means that we have a deficit. In this case, we increase the power production. And if when it stabilizes, yes, it go back to its nominal value, yes, we start to make any additional power. But as you could see here, yes, they are not like in the mirror, yes, because we have an inertia, yes, all the process not are going in one moment, yes. We see that we have a frequency drop, we make a decision, no, automatic make a decision, increase the production, yes, increase generation. And only here we could see, yes, this is the lowest value, yeah, increase the production, stops the frequency drop, continuous increase of production, make the balance positive, the frequency started to rise, yes. And here we could see that the frequency is rising, yeah. So which means that we have too much power on system, but we need to keep it in balance, yes. And we started to decrease production, yeah. But when the system is in balance, it is continue to go to its nominal value. What is very important in this curve, it means that, for example, okay, we have a deficit, yes, and we see the frequency decrease. We started to produce more and got the balance somewhere here, yes? And when we got the balance, it means that frequency stops to decrease, but it is in a position, in a lower position than it is nominal. So we need to produce more power to raise the frequency till its nominal value. Because when we reach a balance, it means that frequency stops with the value at the moment when the balance is reached. So the frequency started to decrease, for example, from 50 to 49 hertz. When if you reach a balance in a time when the frequency is 49 hertz, it means the system is in balance and we keep this 49 hertz. But this frequency is low, it's not a nominal. We need to keep 50 hertz. It means that we need to produce more. So we need to produce more than is in balance to raise the frequency. And when it reach the value of 50 hertz, yes, when we decrease the production to keep this value. This is quite important, yes. So if you reach a balance, it don't mean that you reach the nominal frequency. Balance means that frequency is constant, it's not changing. If we need to go back to the nominal value, we need to cut the overproduction, yes. This is quite important. Okay, this is what I wanted to say. And okay, after this, I think we need to discuss about this frequency, under frequency load shedding. Under frequency load shedding, and this under frequency load shedding, I think it is here. Here it is, part 7. Here it is. Yes, it is here. It is here. Okay. Back to timings. Why to keep frequency is so important, I have said, because if we have not a nominal frequency, it is dangerous to any load or any generator or for any electrical unit, we could conclude. And if it is dangerous, it means we can't keep this frequency not a nominal for a long period. And this figure represents the times and frequencies, possible times and frequencies for the steam turbines, for the steam generators, for CHPPs. What we could see here, First of all, here we could see the frequency, and here we could see the time. And we have two lines for constraints, yes? So here we could operate. Out of red line, we can't operate, and the protection of generator will switch off the generator from the grid. So what does it mean? It means that if we have the frequency, for example, drop from 50 to 48 hertz, it means that we have only 60 seconds to deal with this frequency drop. These generators could be in operation with this load frequency only for 60 seconds. Why? Because it is dangerous for the generator. And if we can't rise the frequency in the 60 seconds, this generator will be switched off from the grid. So this figure represents how much time do we have in any cases, for example, in case of big problems, yes, to deal with these frequency deviations. And as you see, the bigger deviation, yeah, the much lower time we have. All these things are standardized, yes, and we have standards. How many time do we have? And for example, here we have another one feature about the frequency deviation. Standard frequency deviation for power system. Okay, of course, power systems are different with different power. That's why we can't discuss about the power values, but we could discuss the power deviation in a percent. And here we could see, for example, if we have power deviation, power decrease, first of all, because as we understood, if we have overproduction, it's not a problem. We just could decrease the production. If we have a deficit, yes, it means we need to find the power. It's more complicated task. So in this case, we are discussing here only for a frequency drop. If we have only a 10% of frequency deficit, here we could see the speed, yes, of frequency drop in a power system. Of course, it depends on a power system inertia, yes. That's why here we could see a lot of blue curves, red, green, and so on, yes, because it depends on the system inertia and one more parameter, like it is D parameters that calls that the load reaction. Yeah, we just saw when we talked about the static coefficient, the reaction of the generator. The same reaction for the frequency deviation is from the load side. So we could say this is generation side and this is the load side, because generation are electrical units, electrical machines, yes, and the main number of consumers are electrical machines as well. Not, of course, only electrical machines, but all together. And this D coefficient represents the load reaction. I'll find your definition a little bit later, but I need not to forget to talk about this D coefficient. But okay, so here's the main idea is that we see, and for example, if we have a deficit about 50%, yes, so huge, here we could see the frequency drop. Okay, let's discuss about the worst scenario. For example, then it is this one. So we will reach the 48 hertz in about 1 second. And we'll reach 46 hertz about 1.5 seconds. If we come back here, so we could see the 46 hertz. Okay, it is possible to keep for about, I think here 8 seconds, but 45 hertz, it's impossible, yes? So if we will have the fragments of 45 hertz, it means we will lost all the generation. So if we have deficit, we have problems with generation. And if we can't deal with this deficit and frequency drop to 45 degrees, it means that we will lose all the existing generation as well. So the total blackout of the system. In this case, yeah, we will reach 45 degrees in 2 seconds. Yes, if we have this deficit of 50 hertz, so it means that we have only 2 seconds, yes, to deal with the deficit. Otherwise, we will lose all the generation as well. How we could deal? There are two. Okay, so first of all, there is a special automation, what we call under frequency load shedding. Yes, in normal operation, all these fluctuations are covered by this regulator, as we discussed it, based on this static coefficient. So increase more, decrease the production, increase the production. But as it was discussed, we have only up to 5% of reserve. Yes. If we have a deficit of 10%, we can't deal with this deficit using only the regulators, the generators regulators. If we have more deficit, it means that we have problems. Yes, we can't find any additional power. In this case, we have the only one way to keep the system in balance, to disconnect some consumers. Yes, because we can't find any additional generation. In this case, it is a big question how and what consumers we will disconnect. Because in time of problems, we can't make such a decision because we don't have time. And all these decisions are made previously, and automatic knows what to do in any scenario. So now let's discuss how this under frequency load shedding automation works. We need good. Okay, here's some interesting facts. We will discuss them later, but now I want a good feature. Okay, I think I don't have a good feature here. I'll go to find it somewhere here. I need a good feature for discussing. Need a good feature for discussing. This is just another book, but okay, here we could see the same beginning, introduction, and I need this one. Yes, I need this one. Good. A good feature. Okay. There are two ways how we could implement this under frequency load shedding automation. And there are two theories how we could use. We could say there is a West theory, West countries like Europe, United States, and we have the way how it was implemented in Soviet Union and in countries that was a part of Soviet Union. There are two types of such automation. Part one, let we call this one, and the part two. The part two was used only in Soviet Union, in Soviet Union countries, and the countries that studied these, how to say, ideas how to control from the Soviet Union. And now I'll try to explain how it works. Okay, so we have a frequency drop. Here we could see we start our trip for point A. F nominal, it's our frequency of 50 hertz. Yes, we have a frequency decrease. There could be a fault of transmission line. Yes, we could transfer power, yes, to any to a deficit part of power system, or we have outage of power due to fault of power generation or something, or whatever. The main that we have a deficit, we don't have enough power, yes, for our demand. In this case, we see the power drop. Of course, first of all, starts regulators trying to increase the power production for each generator. And if we understand, no, okay, if we can conclude that it's not enough by the continuous frequency drop, the under frequency automation started to operate. And how it works? First of all, it has a start set point. So start set point is based on a frequency. It's a frequency set point. If we see the frequency drop to a set value, it means we need to disconnect a first group of consumers. So it starts from the frequency. For example, if we have nominal frequency of 50 hertz, the first stage could be a set point of, for example, 49.2. But we will discuss, it depends on a power system. So each power system has its own set points, yes? So that means that we have a start set point, yes, when we disconnect the first group. And here we could see, yeah, other set points. That means if the frequency is continuing to drop, we'll disconnect the second group of consumers, and so on. So we have n groups of consumers which are connected to this automatic, yes, and we disconnect in series from the first till the n, yes, groups of consumers. And here we could see, started to disconnect consumers, it means that we decrease this imbalance. And if we decrease the imbalance, it means that the speed of frequency drop decreases as well, yeah? Speed decreases, but it continues to decrease because we still have imbalance, and we disconnect first group in point B, second group of consumers in point C, next one in point D, next one in point E, and here, after we disconnected the third group of consumers, yes, we are in a balance here, because here you could see this curve stabilized and stopped to decrease. We don't reach this next set point of next group of consumer disconnection, yes. Here, of course, are different possible scenarios. This one is only one, yeah, what we're discussing. Scenarios could be different with a different deficit with large power, and this drop could be worse, and any disconnection could help, like it is in a scenario number 1, yes, when our disconnection don't lead to a frequency stabilization, yeah. Okay, but let's continue to discuss this our scenario. So this is a positive scenario, then our automation could deal, yes, with the fault. No, we could say that if we have such problems, this is not a normal regime of power system. This is a fault regime, yes. Because if under frequency automation started to operate, it means that we are not in a normal operation regime of power system. Okay, In this case, we could say some words about also possible regimes of power system. Okay, there are a scheme of an operation modes of operation regime. So normal operation regime, operation mode, then everything happens, yes? If we have some problems, for example, with some faults on transmission lines, some disconnection, and so on, we go to the pre-fault regime. What does it mean, pre-fault regime? It means that system keeps to deal with everything, so it continue normal operation, but it is in a dangerous condition. What does it mean? We don't have a reliability reserve in this condition, and anything what could happen automatically will lead to a fault regime of a power system. So this pre-fault regime is a very not reliable regime, not a reliable mode. We still are in operation, yes, but everything what will happen could lead to a fault regime. And in this case, we see the arrows. So we could come to this pre-fault mode and could go back to a normal, because the relay protection could deal with the fault on the line. Yes, disconnect the line and everything goes okay. We can come back to normal operation. Okay, in this case, yes, if we come to a fault regime, yes, we could come back, because this under frequency automation disconnected the consumers. We are again are in a balance, and we come back to this pre-fault regime, yes? And when we are in a fault regime, we could come back, or we could go to the blackout. What is a blackout? It means that we lost everything, yes? Our power system is not existing. Maybe we could have some islands, yes, with generator. Power system is divided into several islands. In each island, there is a power station, which is continuously in operation, and some loads around this power plant that consumes the generation locally, yes, in this island. But when the power system is separated in different islands, yes, independent islands not connected one to another, this means that we have a blackout, because united power system doesn't exist at this moment. And when blackout happens, the only way when we could deal with all the problems, we started to unite all the parts of power systems to a united power system. Or this blackout could be horrible when we lost every generator and all consumers are in a darkness. Yes, we don't have electricity. So this how all these moves could happen. Okay, let's come back to our scheme. Okay, so we are in point J, yes? When we have disconnected three groups of consumers, and we are in balance for now, but we are in balance with a low frequency. Here is a nominal frequency, and here we are in with a decreased frequency. And as I showed you previously, and we discussed it, we have a time limit for our generators, how long we could be with a low frequency. So we are in a balance, but we have a very strict time limit to be here. We need to go back here. And here two philosophies, yes? For the West countries, to come back from here to here, it's a task for a system operator, for a human being. Operator starting to call to all generators, to all the colleagues, how we could increase the production, how we could find where to buy electricity to go back here. And in Soviet Union and the Soviet Union time, there was a philosophy that we don't need to involve a human to come back to a nominal frequency, because humans can operate quick. They are in a stress in these fault situations, and this is quite dangerous. So let the frequency load automation to continue its work, to continue disconnect consumers, to make an over generation, to increase the power, the frequency to the nominal. So under frequency automation part 1 stops its job when we have the balance in point J, and the part 2 started to operate by a time set point. Here it is time set point. After the stabilization, when it is in balance, yes, in a time like it is a set point, for example 5 seconds, 10 seconds, we started to disconnect groups of consumers that are connected to this automation part 2, and disconnected one group, second, third, and so on, we raise the frequency till the nominal without any impact of a human operator. All goes automatically. This how it works. And here, okay, maybe we could come here to whatever we could. The formulas are the same. And here some formulas how we could calculate set points for this under frequency automation. First of all, the first formula 0.5 let us to understand the minimal possible frequency in a case of deficit. What does it mean? Here in the formula we have parameters like deficit, yep, delta P generation, yes, what we lost, and delta P AAF, it is an under frequency, how much consumers, the power, yes, is connected to the under frequency automation. So all these groups together, what the total power is connected here, what we could disconnect. Kn is this coefficient that we discussed with its formula, yes, and PSL, it's a P load. So what is the total load? What is the deficit of power? How much power is connected to the PAAF1? And we could calculate what could be the minimum frequency with this deficit and with this number of consumers connected to the under frequency automation. In other words, this formula could be the same formula, but it could be transferred to answer to another question. How much load do we need to connect to under frequency automation not to let the frequency goes lower than the minimum value? So we define that the minimum value could be, for example, 46 hertz, yes? And we want to calculate how much loads should be connected to this under frequency automation not to let the frequency be lower than this 46 hertz. And this formula could say to this question, how much loads do we need to connect? In other words, we could calculate the same thing. Formula you could see almost the same for 4.7 and 4.6 are the same. The only difference is how we could understand what the question we're asking. Yes, in this one we asking the question, how much load do we need to connect to the automation not to let frequency be lower. But in this case, we are asking how much load do we need to connect to the automation if we want to need to find the right word, to renew, not to renew. Okay, to rise the frequency. So how to say, to restore the frequency, what I found there, to restore the frequency. Yes, so after its decrease, yes, to what frequency we could restore this in this scenario. So the same formula, but the second question, 4.6, and formula 4.8 is how much load do we need to connect to the under frequency automation part 2. As I said, yes, part 2 is its task is to restore the frequency. And we have, as you see in this formula, yes, total connected loads are separated into automation. The load, the amount of power to the amount of consumers to the part 1 and the amount to the part 2. And here, if you could see how much do we need to connect here, yes, for frequency restoring, this is that formula. And recap, average, we connect to the under frequency automation part 1 about 40–50% of all consumers, and to the part 2 about 12 to 20% of consumers. Okay. And for example, what is next here, it's 4.9 is to understand how much groups do we need. But this formula is quite simple. I want to discuss this question in more details. Yes, so how much set points and how much groups of consumers do we need? Here are some interesting, not here, but here, some interesting information about the structure of under frequency automation in different countries. Okay, when it starts, for example, yeah, first one is some examples for Italy. In Italy, there are 17 groups. Yes, so 17. Okay, come back here. Where is? I want to keep this figure, this scheme. I can, yes. So for Italy, they use 17 groups of consumers, means 17 set points, yes, for every group. And for each group, the difference, this delta F, this one, yes, delta F is different deviation of the frequency drop is 0.1 hertz is set. This is for Italy, quite simple. Quite the same situation is for Latvia, but in Latvia we don't have enough statistic data because we didn't have any blackouts for our power system because it is quite reliable. Yes, that's why we don't have any information to make these set points better. That's why we have a little, no, almost the same structure. We have the same set point step for this frequency drop, and the number, all the groups are the same with the same amount of power. Yes, in Portuguese the situation is more complicated. For example, here we could see the first set point is 49.5 hertz, next one is 49 hertz, and how much consumers are going to be disconnected. First group is, okay, in 49.6, they stops all the pumping hydropower plants, as I said to you about, for example, like it is Kronis in Lithuania. There are some sorts of pumping hydropower plants that could pump up, yes, the water in hours when electricity is cheap, or in hours when we have how to say, from nuclear power plants electricity that we can't consume. Yes, so for this set point they stops all the pumping hydropower plants. In this set point, at the beginning they disconnected 15.6% of consumers. After 150 milliseconds they disconnect more, 18.1%, and in 500 milliseconds 0.7% as well. These very strange set points are based, I'm sure, are based on their experience dealing with possible blackouts in Portuguese power system. That's why they are so strange, but they are very feasible for their power system. So this is the first group divided in two parts, yes, with time delay. Second set point is 48.8, and they are disconnected only 3.9%. In this case, I think, first of all, they're starting to disconnect big groups of consumers, yes, to make the system in balance. And after that, they are playing with small amount of consumers, yes, of consumption power, to make this balance more precise, more accurate. Yes, I think this is the idea. Okay, this is for South African Republic. Okay, they have 4 set points. First one, second one, third one, and the fourth one. In each set point they have 5 groups, like it is here. For each set points they have 5 groups of consumption. Okay, this is for Israel. They have very complicated system as well. Total number of set points 18. There is a starting group and one more parameter that is quite actual. To be true, it is set everywhere. Just we are not talking about this parameter. It is the speed of frequency decrease. Yes. So we are disconnecting the loads not only when we have this, how to say, frequency decrease, but we disconnect when we have a frequency decrease speed as well. For example, how it works, we are not reached the new set point, yes, but we could see that we have a high frequency decrease speed, and we could start to disconnect faster, quicker, not reach this next set point. This is the idea. Okay, for example, there are some data for India as well, but India is quite a huge country, and this is quite simplified. Trying to see. Okay, so the start set point is 49.5. Yeah, not much information because it's quite complicated. Just the starting set point and the idea that the under frequency automation stops its operation when the frequency is in is from 49 to 50 hertz. So with the idea, yes, that the under frequency automation goes something like here. So they don't have, sorry, you don't have uh, additional, this separation of this under frequency automation part 1 and part 2, but this part 1 is works like first and the second one, so it stops, yes, to operate when the frequency is increased. It's starting to, how to say, reveal, yeah, to its nominal value. Okay, and next, what we are going to do today, it could be, I'm thinking where this could be. I want to discuss an Italian blackout in the year 2003. Very short. That's why I'm not using the English version of a report, because it's huge. If you're interested, you could read it. I have one student who wrote a master work. Yes, he analyzed this blackout, and he have some tables with how to say, short summaries about what happened. That's why I'm going to use his master work. I want to find his okay, it is bachelor, it's his master. This is bachelor. Okay, I need master work, master. Yeah, master. Okay, let's go to Italian blackout.
Is there any student in bachelor's they are studying in English?
Sorry?
In our course, is there any students are studying in English in bachelor's?
Yes, of course. For example, for us, okay, for example, you are not a typical student, because you understand you are the only one, yeah, for now in the masters, yes, but for bachelors, we have a group of students in English. So, but this is a local student, that's why these summaries are in Latvian, but we need, how to say, just facts with digits. Okay, need to, okay. So as I said, there are a lot of reports in English about Italian blackout, because, okay, this blackout was very dangerous, and everyone tried to, how to say, to analyze this blackout. So yes, I'm just going to use some small, okay, this is the map. Okay, so first of all, it happened in 28th of September in year 2003, yes. So what we have, first of all, the map of Italia. Okay, so as you know from geography, yes, Italy is connected to the Europe, yes, via several border countries like France, Switzerland, Austria, and Slovenia. Italy by itself is a deficit country, so they can't produce enough electricity for their demand. That's why they're buying electricity quite a lot. Let's see the interconnection here from Italy, yeah, interconnection lines, Italy, France, Italy, Switzerland, Italy, Austria, and Italy, Slovenia, to neighbor countries. Okay, here it is. Okay, so 380 kVs, 3 lines to France, 2 lines to Switzerland, and 1 line to Slovenia. 220 kVs, 1 line to France, 6 lines to Switzerland, 1 to Austria, 1 to Slovenia, and 500 megawatt DC cable to Greece. This is the interconnection, so quite good. A lot of lines you can see here. And what about the consumption and the import. Here you could see the total demand, total consumption of Italian power system. It is 27.4 gigawatts. But as I said, it is deficit power system. And for the time of blackout, its deficit was about 7,000 of gigawatts. And let's see how this deficit was divided. So to a power from Switzerland, 3.6 megawatts, power from France, 2,000 megawatts, power from Slovenia, 0.6 gigawatts, power from Austria, 191 megawatts, and power from Greece, 300 megawatts. Yes, so. And one very important parameter, it's a maximum temperature for wires. Yes, for transmission line wires. Why this is so important? Because from this overload disconnection, sorry, I'm wrong. Okay, the scenario in 29th of September, night time, 3 o'clock. One of the line, transmission line, Italy to Switzerland, we could see that there are 2 transmission lines, yes, Italy, Switzerland, with the voltage. It was how to say this, the load of this transmission line was 86%. And due to, this is a quite high load for this line, yes. Due to this high load, the length of the transmission line decreased. You understand this physics, yes? The more power we transmit, it means the higher current is flowing our wire, yes? The higher current value, more heat. And due to this heat, the length of wire increase. Yeah, I think you should know this process, yes, about the temperature of wires, yes. And due to this increase of the length of the transmission lines, the line touched a tree under the line. A quite standard situation. That's why we know that we need to cut all the trees and bushes under the lines. Yes, it's a standard practice that we are keeping these lines of, but in this case, due to the decrease of the length, yes, it touched the tree, and of course, it's a fault. Yes, it's a fault, and relay protection disconnected this line. Of course, try to reclose this line, but without a success. As a result, it means that we lost 1 line. So we know that from Switzerland, the total power is 3.6 gigawatts through 2 lines. We lost 1 line. It means that we have only line in operation. In this case, that this line, this one line that still is operation is overloaded because it keeps all the power from the disconnected line. And in this case, it was at 3 from the morning, 3 o'clock, 1 minute, and in 24 minutes, the second line, Switzerland to Italy, was disconnected by the overload protection because the transmission line was overloaded by 110%. So in this case, we are lost 2 lines. We are lost connection to the Switzerland. Yes. And how it happens? We still have the same demand in Italy, but we have disconnected 2 lines. It means that all other lines that are still in operation should continuously transmit the same amount of the deficit. That means that The first line is disconnected by the overload protection. In some time, second line disconnected with overload protection, and so on. In the case, okay, this started. The overload protection started to disconnect lines at 25 minutes, and here we could see in a series the same operation, and in 25:42 seconds, Italy is disconnected from the continental Europe at all. All the interconnection lines were disconnected. So the process started at 25 minutes 25 seconds. Oh, sorry, 21 seconds, and all the lines was disconnected in at time 42 seconds. It means that we lost all the interconnection lines in 21 seconds. So all the process started with only one line, and after we lost these one transmission lines, yes, we had here 25, almost 25 minutes to do something, but nothing was done, and because all this time other lines was overloaded, and in 21 seconds all the other lines was disconnected by the overload protection, and as a result Italy is disconnected from the Europe with a deficit of 6.9, almost 7 gigawatts. So total consumption is 27, but we have deficit of 7. What to do? How to cover 7 gigawatts of power? Good question. So I want to see the, okay, I want to show this one. I want to show this one. So what we see here, yes, it is 325. This process is, here we can see frequencies, see time. This one is imbalance, this is frequency. So in this time, overload protection disconnect lines, yes, and in this moment all the lines are disconnected, and Italy has a deficit 7 gigawatts. We have deficit, we have frequency drop, huge frequency drop, because if we, how much we have, 7 from 27, how much it is? Where 7 from 27, we have a deficit of 26%. Yes, under frequency is the only way. All the regulators tried to produce more power, but as we discussed, it's about 3-5%. It means that we have 20% of deficit, and the only way is started to disconnect consumers to keep the system in balance. And here we could see the start of under frequency automation. It started to work, yes. The imbalance started to decrease because we are disconnecting consumers, but we could see here all the time that we are starting to disconnect consumers, frequency is continuous to, because imbalance is still in life, yes. And here imbalance, we see that at this time we have disconnected by the under frequency automation enough consumers to keep the system in balance. Here you could see system is in balance, but as I said, we have a system in balance, but frequency is low, is lower than 48.5 hertz. And in this case, we are in a big problems with, why? Because we could start to lose our generators frequency at any second. And this happened. And this happened. We are starting to lose our own generation due to low frequency. And here we could see a list of generators that we lose. Some recap, some summaries. Okay, so Italian power system, okay, what it lose? It lose 3 generators with a power of 900 megawatts due to low voltage. They lost self-consumption bus, steam boiler can't produce enough steam due to frequency decrease because it is very close. So if you have lower frequency, it means that you are producing less power. Because how it works? What is the frequency? What frequency shows? Frequency shows because you know our voltage is a sinusoidal voltage. We have a 50 sinusoids in 1 minute. What does it mean if we are talking about power? It means that we have 50 power, how to say, impulse in a minute. And if we have a frequency decrease, it means that we have not a 50 power impulse in minute, yeah, but we have 49 power impulse in minute. So the amount is this, not amount, the value is the same, but the power frequency is lower. It means that we don't get so much energy. You don't get 50 power impulse. We get only 49 power impulse, and by this the motors, pumps, very important parts for the power station pumps, started to produce less steam, and as a result less power. So here we lost 3 generators. Here we lost 2 generators with power of 300 megawatts. This case they had problems with air pumps, yes, because it's when it's CHPPs burn fuel, yes, to produce power. So they have air pumps problems. Here they lost 2 generators with power 700 megawatts. They had problems with oil pressure in a system, and so on. So here you could see the number of generators and total power that they lost. Here you could see a huge number. Okay, so let's come back to this. So under frequency automation done a good job. System was in a balance, but unfortunately due to a low frequency here we started to lose generators and frequency drop continues. By the way, we had more sets for the under frequency automation and more groups of consumers that we could disconnect. And by all this time, yes, when we lose generators, we continue to disconnect consumers to keep the system in a balance. But this is very dangerous. We are in deficit and we are still losing generators, yes. And as we know, the number of consumers that are connected to the frequency automation is limited, approximately up to 50% of total consumption, yes. And as a result, when we disconnected all the consumers connected to this automation, we see the next frequency drop because we don't have what to disconnect. And as a result, in this time, we had a blackout for the whole Italian system. So what was wrong? The main idea then, at this point, when we make the system in balance, we stopped to disconnect consumers to increase with an idea to increase very quickly increase frequency to keep all the generators in operation. But due to the specific of this automation in Italy, yes, as I said, to increase the frequency is a task for a system operator, for a human, and human, it was, you understand, it was 3 o'clock, it was night, yes, at the night time. People was in stress by this horrible situation, and they just don't have enough time to make decisions, to make calls, to disconnect consumers with an idea to increase the frequency. So they just didn't have enough time in this point, yes. Then they have a balance to disconnect more consumers and to rise the frequency, quick rise of frequency. They were in this balance with a low frequency too long, and they started to lose generators. That's why, from my point of view, when we have automation that restores frequency quick and automatically without involving a human, is the best idea, it's the best solution. Don't let a human make a decision and something on in a stress. Let's make an automation to deal with a problem. That's an idea. So I think this is our last case for today, and I'll just didn't have enough time to prepare tasks, so we discussed today 3 topics.
Our inertia.
Inertia, yes, this concentrated static coefficient for regulators, and the third one is this under frequency automation. So I'll prepare for you 3 tasks for your homepage and send via email.
Okay.
So as I said, okay, this will be your homework. I have one question to you. Do you have a MATLAB, and do you have any skills with a MATLAB?
I don't have MATLAB in my system.
Okay, but what about your knowledge and your skills with MATLAB?
Yeah, I have done some experiment in my bachelor's studies.
Okay, why I'm asking, I have it's not okay, it's not maybe a MATLAB, it's part of MATLAB, like it's a Simulink, it's a simulation environment of MATLAB.
Yeah.
I have schemes. I have 4 schemes.
Okay.
You don't need to, how to say, make any schematic. They are done. You need to try to change parameters of this scheme, like coefficients, because all these schemes are this okay, not this, but okay, where it is, all schemes are these regulators that represents power systems with parameters like this inertia, this R coefficient, and so on. And your task will be to try to change these parameters and to write the analysis. So what will happen if we change these parameters? So just an analytical task, yes. So schemes are ready made, yes. You just need to play with the parameters and to see what will happen with frequency.
Okay.
So this will be your task. So, but
And
to run these schemes, you need MATLAB and Simulink as well.
okay.
So that will be your one more task to install MATLAB. So you could use this student version. Yes.
Yes, I will try to install the MATLAB in my system,
Yeah.
and
Yeah.
yeah, that is enough.
Yeah. And so, as I said, so okay, to get how to say a mark, so you need to make your homework with tasks, as we hear, yes, done today, and to deal with MATLAB schemes. But
Okay.
I'll explain what to do later when we finish
Okay.
with your homework. Okay, so I think it's all for today, and I'll put this record to YouTube. So
Okay.
you
And
could watch.
I need this link. I lost the link already.
Link to
Link
YouTube.
for the this no document.
Okay, I'll better send you documents. It will be, I think, easier for you. So I just
Fine.
sent
Yeah.
you documents. Okay, so okay, so I need you to send when we discuss it. I need part 6, part it's a 4, I need 3, I need 4, yes, so I just not to send you okay, all these tasks are here. Okay, I need to send number 4, where it is. Okay, here it is, 4. It is open. Okay, I need to close it. I need to close it first. I don't want to save the change. Okay, so I can send it now. Okay, this was with tasks, inertia, and this coefficient, static coefficient, and this one. Okay, so it is opened. Yes, number 6, number 6, number 6 here, and this one is okay. I'm tired. Sorry. Do the same mistake. I need to close and then send. Okay, so the first one number, it's for part 4. Yes, it's for first 2 tasks, and for the under frequency automation, formulas are here. In Latvian, this under frequency automation calls AAF. Yes. And they're just, how to say, with the same information, but just from 2 different books, because they have different features. Yes, and I used both features to show you. So I think this is all you need, yes, for these 3 tasks.
Okay, Professor. For the first task, I need to calculate the power inertia, and the second one
Yeah,
is
I'll prepare tasks for you and will send. So you could use this record and this book with formulas to make the calculation.
okay, Professor. And please send me the web link for the all documents.
Okay, the web. Okay, all these documents are here, but okay, I'm tired. I'm pressing wrong buttons.
Yeah.
I need chat where it is. Okay, so this is a
And
link.
okay,
This is a link, and the book is here. This how this book calls.
and
So you could find all the materials here.
okay, Professor. And what about the examination for this subject for the course? Final exam, is there any exam for the 2 credit paper?
For you, you need to do your homework and this model
Task.
description, and this will be enough to get the final mark.
Okay, Professor. And
So we'll
about the
go for, how to say, for an easiest way.
yeah, and about the practical placement,
Sorry, what?
about the practical placement internship.
Ah, about the internship. Okay. What
When will
about the
the final
internship?
examination?
Yes. I'm thinking. I need to we need to commission this your internship, but you go with other students. So it means that it could be, I think, in January.
Okay, professor.
So you need to, how to say, present, yes,
Okay.
make to present your internship. I think I'll write you an email when we will be ready, because how to say, all students goes together, from bachelor, from masters, and from foreign students as well, so all at once. So I think it will be in January, I think, because
It
it
is
depends. You see, this date, it depends on the agreement, because when students will finish their practice, because everyone have different, how to say, end data for the practice. So due to this, I think it will be in January, maybe in the middle of January, I
it
think.
is in online or it is in person?
Quite difficult to say, because the last time when it was in September, I made it, it was in parallel. We have some students from different cities online, and some students was live, yes. But
Okay.
okay, we have a new dean from the August, yes, because we will have a new faculty. I don't know, we will have a new united faculty for the computer science, telecommunication, electronics, and energy. Yes, and we will have a new dean,
Okay.
and it is quite complicated to say what the rules we will have next.
Okay.
So it depends on the rules. If we will have a possibility to make it online, I will make it in parallels. Who wants to come live, and some who are far away online. But maybe it will be impossible to do it online. Maybe we will have a rule to be only, how to say, live.
Okay. And
So
about the
I can't answer your question for now.
okay,
Yeah,
okay, we can discuss after the January first week.
yeah, yeah.
And about the relay
Okay, for
protection.
relay protection, as I said, we'll start with relay protection when we finish this subject, yes.
Okay.
But I have still some questions, because the responsible person from your foreign student department said me that you don't have this, how to say, this subject in it is 715 or 713, I forgot, in this semester. I need to discuss this to this responsible girl from foreign student. I don't know. As we
Yeah,
discussed,
there
I
is
think you said that you
the
have all three subjects now in your list,
yeah, yes,
but she
professor.
said that you don't have. I don't know who is true. She said that you have for now only this lecture about this relay protection, but you don't have this subject with task with 1 credit point. I forgot, it is 0 point. Okay, so let's go to Agnes. What she wrote me. Yes, she wrote me that you don't have this EES 715.
Yes, I don't have that.
Yes, but in, how to say, this EES 715, it is how to say, subject when you have a mark for the practical tasks.
Okay.
So in this case, I will discuss to Dolgitzer, because you see, we have that lectures and this practical, this is, how to say, one subject just separated for two professors, yes.
Yeah.
But the total work is, how to say, the same, because without the lectures you can't do your practical tasks. Yeah,
Yeah.
so first you're listening and make this practice. So I need to discuss with Dolgitzer how we deal with this. But I think we'll go in a standard way. I'll make tasks for you. You'll make the tasks, and you will just get your mark when this subject appears in your list.
Okay.
And you will have the same mark as for
This is for
subject.
the 715. It is for which subject?
It is relay protection practical task. So
Okay,
you will
okay,
have
okay.
the same mark for two subjects, one and
Okay.
the same for the lectures and for this 715.
I
Because you
understand.
know you have for our students we have a very simple formula. The total mark is mark for this practice and mark the average for practical task and for the exam. In this case, I think Dolgitzer will not make an exam for you. He will say that you need to only to do the practical tasks from me. So in this case, it means that you will get 2 same marks when you will make my practical tasks.
And but in my credential,
Sorry.
in my autos.
Yes.
Wait a minute. I will check. And here, the principle of productive relay of electrical system. There is mentioned 4 point.
Yes.
And
yes. And yes, from Dolgitzer you have lectures and an exam. But I think you will not have an exam. You will have my practical tasks.
Okay.
And when you finish my practical task, you will get a mark for this 4 credit point subject.
Okay.
And as well for the subject EES 715.
Okay.
When it will appear in your list.
Okay, Professor. Yeah. Okay, we will go by step. First, we will complete the control system. Then we will go by that is good enough. Thank you for your time spending for me, Professor.
Yeah. Okay, it's okay. I'll stop the record and I'll try